And now it's my joy to bring up Markus. So Markus is a principal research software developer at Microsoft. So let's welcome him with a round of applause. Take it away, Markus.
Hello, hi there. Folks, I'm not at my best because, so I pre-recorded this talk yesterday. Enjoy and see you afterwards for the Q&A. Hey, welcome, and thanks for having me. Yep, my name is Markus Kuppe, and I'm a principal engineer at Microsoft Research. And today I want to show you a methodology, not just a language, not just a set of tools, but really a methodology that engineers at various companies, big and small, apply to design, build reactive systems /distributed /cloud microservice systems, making sure that these systems live up to their expectations before the first code gets written, okay? And the high-level outline of this talk is that I would contrast this idea, this methodology, to the contemporary art of building distributed systems, where we write tests and then we debug our system into production. So what does our average distributed system look like? We have a front end, a number of web servers. We have a client, HTML, JavaScript, that on behalf of the user sends a request to the web front end server, the worker, front-end worker, which issues the user request to the backend. And since they are decoupled, the backend and the front-end, the backend that handles the eventual user request, we have a database for persistence. So that once we've written it to the database and acknowledged it to the user that we successfully wrote to the database, our front-end can crash, because it's stateless. It doesn't matter. We can also scale it up later, as we will see, when the data is in the database. Because our front-end and our back-end are discovered in a modern architecture, we need something like a message queue connecting the front-end to the back-end. Maybe this is part of your database, maybe not. Here in this architecture, we have two entities. We have the database and we have a message queue that the front-end uses to send a notification to the back-end once it's written the real data, all of the data to the database. And on top of that, we're going to build a fancy web shop that is going to sell pierogi. Where I'm at, it's very difficult to get access to authentic pierogi, so that's why we definitely need this kind of system here, where I can place an order for pierogi, and then the front end accepts the order on my behalf, writes it to the database in the second step, gets the acknowledgement back from the database once the value has been written and is durable in the database. After which point, number 4, it publishes the message in the message queue. It notifies the backend, look, there is a new order and here's the order ID. And then the backend at some point later in 5 receives the message from the queue, reads the order ID, with that reads the order from the database and fulfills it. We all like our architecture diagrams. Here's the architecture diagram for this system. We have the front end, first step, write to the database, another given order ID, get the ACK back. If the ACK sets success, enqueue in the queue, push the notification out to the backend, which reads another given key from the database and gets the response from the database back, including the metadata, all of the data related to the order. And I get my yummy authentic pierogi. So what would it entail to build this kind of first prototype for this system? Well, first of all, we have to get a cloud subscription, right? These days, we no longer host infrastructure on-prem. That's way too expensive. Everything in the cloud. It allows us also to scale up and scale down if necessary. Why do we need this subscription with a sufficiently funded credit card? Then we have to log in and set up all this infrastructure, come up with a deployment of it, right? We need a front end, we need a database, we need a queue and a backend server. Maybe in the tests, in the first prototype, the front end runs on my machine, but we definitely want a database, we definitely want a queue and a backend server. And then and only then we can really implement our workflow and deploy it to the infrastructure. And then last but not least, The most difficult part, I argue, is testing it. Yeah, testing the hell out of it to make sure that it actually works beyond just the happy path. And if you think about it, since we use all this third-party infrastructure, it's very difficult for us to do anything else except end-to-end tests. We can't really mess with the database, hoping that we can distort it so that we deviate from the happy path. Anyway, let's see what this code looks like. So we head over here to our favorite IDE, and I have a bit of boilerplate. And this I wouldn't even call what we're going to write. I wouldn't even call it a real test. Instead, this is sort of the prototype of a prototype. It's really, really simple in the sense that we write to the database and then see if we can, in the other region, in Eastern Europe, where it's the only place where you can get authentic pierogi, you can read the value from the database again. Okay? So we need two database connections, two database clients, WestUS, and oh yep, our AI-assisted programming gets most of the job done. Endpoint discovery enabled is what it's missing, but that's fine. Okay, that's the first database connection, and we need a second database connection, but I guess, oh, here it goes, but I'm going to copy paste this one and just rename it to Poland Central and change this to Poland Central. Okay, so now we have our two database connections. Great. One mimicking the front end, WestUS, where I'm at. The other, Poland Central, where we have pierogi, mimicking our backend. And then the workflow, in quotes, is that after we kind of created the containers and some database foo that has to happen, this is also what we could have generated with our AI copilot. We do step number one. We create some order, some random order, some dummy order that has a string in it, some random string. We write it to the database and wait for the response. Does the database acknowledge this write? Here, I don't even bother to handle the case that the write fails. I just assume it succeeds all the time. Otherwise, we would have to handle an exception and do something sensible with it, right? And because when I wrote this talk, the content of this talk, I realized that introducing the queue adds way too much complexity. That's why this very, very preliminary test skips even the queue. Yeah, we skip the part where we publish a notification on the queue that notifies the backend. Instead, we just here sequentially have the backend read from the database. And it reads with the order ID that the front end wrote it under. And the very, very super basic, almost clumsy consistency test is that we compare the value that the front end wrote to the database to the value that we read from the database. That's it, right? And if for some reason these two values are inconsistent, they're not the same, then we know we are using the database incorrectly, right? Because this is the one thing we cannot tolerate, that we write an order to the database and that it doesn't come out on the other end. So let's see, we can run this. There's a run button somewhere up here, and assuming nothing else fails and the infrastructure in the cloud works fine, we can write value into the front-end database in WestUS, and we can read the same value in Poland. Yeah, and this has happened now 50 times and keeps increasing. So how long do we wait? Yeah, we can keep it running, and then obviously we can go and grab a coffee. I believe it's coffee time at your place right now, and that's like one of the most famous XKCDs, right? Oh yeah, we're not slacking off, we're testing our software. Okay, then carry on. But here we won't be slacking off, sorry folks. Instead, what we will do, we will use this other methodology that I promised on the opening slide, to model the same thing we just did in the code, okay? And because I know that you don't speak TLA+, and the language looks a little bit different from the language such as Java, Python, C++, or some functional programming language, I extracted everything that's relevant into slides. So first and foremost, what's important is our model has 5 variables. The log, which represents the database. The front end, here represented by 2 variables. The requests, those are the ones that the user still has pending. And a future that we can check whether or not our database write succeeded. We have a variable that represents the backend, the set, the collection of all the values the backend will eventually have read, and our message queue. Okay, 5 variables in total. Now let's look at the first 2 bulletin items from the second slide that are encoded here. So the front end write, the user requests comes in, it gets written to the database. This can happen as a precondition if and only if the future here is nil. Yeah? There is no other write by this front end going on at this point. In which case we can write it to the database under the given key, the given value. And the database returns a future to us that we can check later whether or not this write succeeded. And the other 3 variables, requests, queue, and backend, do not change. Yeah? Nothing else happens in our global perspective of the system. The log is inside right in it. Okay? The way to think about this piece of 1-2 front-end write is that it's kind of akin to a transaction, which either happens or doesn't happen at all. And if it fails for some reason halfway through, we don't really have to compensate. It's all sort of automatically rolled back. That's all part of it, of TLA. This piece of action/transaction happens all or nothing. And the request prime, queue prime, backend prime, future prime, log prime, they define the state of the global system of the queue, the database, the front end, and the backend in the next step. Not just the state of the front end, not just the state of the backend, but the state of all the entities in our architecture. So with that, let's move on to 3.4, where assuming there is a pending write, an ongoing write that the database has not yet acknowledged, and the database now acknowledges it. This write was successful. Well, then we, in turn, the front end, we can acknowledge the write to the user by removing it from the requests that the user has still pending. Yeah, we remove this particular write, this particular request/order from all the requests the user gave to us. And because there's one less item now, the user knows, okay, this has been acknowledged. Need some fancy UI to communicate to the user. This is outside the scope of this model. And then as in the same step, in the same transaction, atomically, we write to the database. We append this notification message that contains the key, the order ID to the queue. And the future gets reset to nil so that the next user write, front-end write can happen after this transaction finished. The unchanged really is just syntactic sugar for log prime equals log and backend primes equals backend. Again, the log, the database, and the backend do not change when a 3.4 front-end enqueue step/transaction happens. But the backend changes, it does change in the next step, in the final 2 steps, 5 and 6, assuming given that the queue is not empty. Yeah? not empty queue. Well, then that means there is a message in the queue. So let's pop the head element from the queue. The oldest message in the queue, name it MSG, and then with the key that's part of the message, let's read from the database. And whatever order we read from the database, let's add it to the collection of all orders in the backend. And then finally, remove the consumed message from the queue by only keeping the tail of the queue in the next state. The log and the front end requests future does not change. So this gives about approximately 20 lines of TLA plus here that capture all of what we did in the Java code, plus we also deal with the queue here, okay? And it's approximately the same ballpark when it comes to like size, lines of code. With bigger systems, more complex systems, usually the size of the code blows up way faster than the size of these specifications. But there's one thing missing here in these slides that we had in the implementation, which is, let's see, our test. The front end write equals the back end read. This is not yet in the slides. But before we continue, I just noticed, ooh, after 1800 reads and writes, there is an inconsistency issue here. Something is broken with our code. Those of you who have dealt with distributed database and know about consistency levels, you can pinpoint this, I'm sure. The others, let me continue and I will explain to you. But there's something wrong with our code. It only took 1800 cycles, write and read cycles for this to hit. No idea how long it will take the next time we spin this up though. So let's head back to the TLA plus. And let's add this one missing piece, this test that we have in the Java code, right? So the test here looks like this. It essentially says that all the acknowledged requests, this here are all the acknowledged requests. The backend contains them. And now the question is, when does it contain them? Well, it contains them eventually. This diamond operator here says that request value for all acknowledged requests will eventually, at some point in the future, it doesn't take forever, a finite amount of time in the future, will request value be an element of backend. Well, how long does it take in terms of work clock time? We don't care, because we don't really know, right? Now imagine coming up with this test in your implementation. You don't know how long to wait, right? You could wait forever, but then if the request never arrives at the backend, then your test will just wait forever. Yeah? So you have to time out at some point in order to do the next test, of which you undoubtedly have many. So you have to give a timeout in your test. But what now happens if you give a too short timeout? Because it's very difficult to predict how long does it take for the front end to write into the database and then for the queue to process your message before it arrives at the backend, which yet again has to do another backend database read. It's very difficult to estimate this in terms of work clock time at one of the various processes of the system, right? So if we give too low timeout, then our tests become flaky and we have these false positives, right? These tests that fail intermittently because the timeout ran out, even though the request eventually was read by the backend. So timeouts are brittle. Here we don't have to deal with timeouts. Here we can just say it happens eventually. And if it doesn't happen in a finite amount of time, then that's the failure. So let's see if we can also use this TLA plus model here to explain the inconsistency that our unit test just confirmed after only 1800 cycles. So this is our specification. There's a bit of boilerplate here that I omitted. Yeah, in total it's 120 lines of TLA. But we've seen this, so let's just check this model and check whether or not this test passes. And what happens is, oh, this test also fails. Okay, with knowing that the code level test failed, we kind of expected this to fail, right? But this failed after less than a second. We didn't have to wait 1800 cycles, it failed immediately. Well, but maybe this was just like damn lucky, whereas our unit test was not unlucky. So let's check this again. And once again, this finds the violation, the test failure, after less than a second. And if you look closely, these statistics here are exactly the same. No matter how many times I check this, it will always find this error in the same amount of time after the same amount of states explored. And that's not it. It also finds the shortest error trace from the beginning of time, from when we booted up our distributed system conceptually, to when the system crashed. In this particular model here, it took 10 steps, well, 11. Ignore the stuttering. Initially, we can see the value not just of the front end, not just of the log or the queue, we can see the value of all the variables. At the front end, at the back end, at the database, at the queue. And we can also see the state of the system in the state that violated our correctness test. So what happened here? Well, let's see. So the backend apparently read no value, whereas our request is yummy pierogi or more pierogi. Well, it read something that's like a 404 or models the database returning something that says, hey, I don't have a value for the key that you've given as part of your read. So the database essentially said this failed. This is bad, which is especially strange given that the log, the database, seems to have this value. It has yummy pierogi and it has more pierogi. So why didn't it serve it? Well, like I said, those of you who are familiar with consistency levels, we are using the wrong consistency level here. Eventually, consistency is very difficult to deal with, and it exactly leads to these kinds of anomalies. Even though the values in the database does not necessarily return it as part of the read, causing to this inconsistency here. But let's zoom out and again look at this. We get a counterexample that from the beginning of time contains the state of our complete distributed system, of the values of all the variables in the global distributed system. Contrast this to debugging a distributed system where you log into this individual node, you get the perspective on this individual node and have to piece together the global state of the system from looking at various local nodes. Very tedious and very difficult. You can't rely on timestamps because clocks aren't synchronized and can never be completely perfectly synchronized. So this has tremendous value, and there's not a single piece of logging in our specification. There are no log statements here it could either be A, incomplete, and B, also buggy, logging the wrong thing. It's all in here, perfectly consistent, without a single log statement. Great. So what's the fix? The problem is obviously, getting back to the consistency levels, that we write to this database in West US, and there's a bit of synchronization, replication going on between Poland and West US. And if this synchronization happens to be too slow in the real world, in the real database, then the read here that races against the synchronization, if the notification is faster than the synchronization replication, then this read here in step number 5 will inevitably fail. And this is what happened in our test case after 1800 reads. We were lucky. It only took 1800 reads for this to fail, confirming to us that there is a bug. So what's the solution? Well, we can go into the code and switch from, where is it, eventual consistency to what we call strong consistency. Read operations always return the value that was last written. That's great, that's exactly what we wanted, right? I could test this now again, but the question remains, how long do we wait? How long do we wait for us to be sure that this change is actually correct? Instead, let's do the change here in our model. Run this, check model, and the machinery says, yep, everything is fine. There are fewer distinct states, there are fewer behaviors because we are using strong consistency. And this works. And this is not just testing where we explored randomly generated executions and with bad luck only ever generated one particular execution that happens to be correct, but the next execution that we were unfortunate enough to not generate fails. This here generates all the possible executions, as I will show later. Okay, so strong consistency works great compared to eventual consistency. But there's a problem because we want our web shop to operate at scale, right? It's easy to spin up more front-end workers. It's easy to spin up more back-end workers because they are pretty much stateless. We can just add any number of them. Scaling up the queue and the database is not so easy, right? They are more or less singletons in our architecture. We can apply some sharding technique, partitioning, but that's also going to take us so far. At some point, if we are super successful, we have to relax our database consistency to keep up with demand. We explored eventual consistency, and because it's the fastest in terms of latency and throughput and also availability, that's probably the reason why our AI Copilot suggested to use eventual consistency initially. But it causes these inconsistencies, these anomalies that we cannot tolerate in our web shop. So we can't use eventual consistency. We can't use strong consistency because it's on the other end of the spectrum. And if we want to scale up, this is not fast enough. So let's settle for the middle ground. Let's use session consistency. So what's session consistency? We hack in session consistency here. What does it say? Consistency monitoring reads and read your writes, a bunch of technical foo here that may or may not make sense to you. But we can just change the API to use session consistency and once again run our test case and wait for it. Maybe it's finally time to grab coffee. Obviously not, right? We go and make sure that reading under session consistency in our model confirms that things work. The test is going to pass. Check the model. And whoa, no, session consistency does not work. There's something amiss here. What's the problem? Well, in the interest of time, let me take a shortcut here. Some of you might notice that this looks awfully a lot like the statistics we saw for the error coming out of eventual consistency. Same is true for this error trace. It's exactly the same error trace. So what's the problem? The problem with session consistency, like the name implies, it's consistency per session. And we have to pass a session to the database read. Because the read is now happening for a particular key K and a token, session token T. And the token we use here is the nil token, because we don't really pass the actual token that the front end used to write the value to the database, or we just pass the dummy token. So let's change that. Let's change it to future here, which is the token we need in the backend to read the value again. And with that, everything is green. Although notice that the number of distinct states is slightly bigger than the number of distinct states with strong consistency, which is because session consistency allows more executions, which is why it's faster, allows more throughput and lower latency compared to strong consistency. And we can see these behaviors, these properties of strong and session consistency by looking at these numbers here, these statistics. Okay, great. Session consistency it is if you pass the session token. I can tell you that sometimes people forget to pass a session token, and then this causes a major outage. But now, pants down, because so far I haven't shown you the database code. And clearly, all of this is easy if you have like a sophisticated database emulator. I can tell you there is no such database emulator, at least not for the database that we were using here. There might be a database emulator, but the one that exists only supports strong consistency. It doesn't support the other consistency levels. Here in our work, we observed that a database, well, is just a global log on steroids, right? It has various different APIs, NoSQL and Gremlin and whatnot. It provides different consistency levels and a lot of other features like durability and so on, transactions that are very convenient to use. But from a client perspective, a database is just a global log that we can write to and read from, more like a key value store, right? So with that insight, we can abstract, and this is what TLA Plus is about, can abstract the database into just 200 lines of code that require 4 variables, and most of the magic is in one read operator. That's what this read operator looks like, and I don't expect you to be able to read this, right? This is a bit too sophisticated for somebody who sees TLA Plus for the first time today. If you want the nitty-gritty details of how we did it, there's a paper out, Understanding Inconsistency in Azure Cosmos DB with TLA Plus, that my co-authors and I, Finn Hackett and Joshua Rove, wrote, that explains how we modeled the database in just 200 lines while preserving the anomalies of all the consistency levels of this database. But this talk is about TLA Plus and not about a database, a particular one. So how is it possible to model such a database in TLA Plus in just 200 lines of code? And the key answer to that is that TLA Plus has first-class support for non-determinism. In a programming language, there is no such thing like non-determinism. Everything is deterministic. And everything that doesn't appear in the programming language might behave non-deterministically. The scheduler behaves non-deterministically. The nodes in your distributed system behave non-deterministically. They might crash. In TLA Plus, this is all part of the language, or can be modeled with the language because it has first-class support to model non-determinism. And then, once we have modeled all of that, using the syntax for non-determinism, we get a state graph out of it. Yeah, think of a graph that contains all possible system executions. Yeah, this here is the state graph of our system. Gray state is how it starts, and then initially there is no alternative. We can only move forward and write to the database. But at that point, there are already 2 alternatives. Either this happens or this other thing happens. And then the next step, there are again alternatives. And all of these represent possible system executions that an implementation could take. But in TLA Plus, since we have this graph, we can use tools that analyze this graph. And for example, look for a path through this graph where there might be a cycle where a desired thing, our test, fails forever. In the cycle, never our desired test passes. And then it can issue a failure and show this error trace that we saw. Okay, so who uses TLA Plus? There are a few names up here. Those are mostly bigger companies. The smaller ones are not as outspoken. The bread and butter of TLA Plus applications are consensus algorithms such as Raft or Paxos. Pretty much all of them have been studied and analyzed and sometimes even proven correct with TLA Plus. Distributed database vendors such as Microsoft and AWS and Mongo use TLA Plus to model the internals of their databases. Here we model the client perspective. They use TLA Plus to model the internals. There are multiple replicas that have to communicate with each other to sync up and so on. Hardware companies use it to model cache coherence protocols in processors. Others have used it to model network protocols, peer-to-peer, whatnot. There's a plethora of examples in the area of concurrency primitives, queues, critical section algorithms, glibc conditional variables to make it a bit more technical. People used it to model cloud security, software-defined perimeter, and whatnot. We, the people working on TLA Plus, also use it to dog food. We use TLA Plus to develop the TLA Plus tools, one of the tools we use in this presentation. And on the other end of the extreme, some people apparently even find it useful to model biological processes such as polymerase and chain reaction, PCR, that we've all heard too much about during the pandemic, right? The reason why consensus distributed databases is the bread and butter of TLA Plus is because of the fact that TLA Plus' creator is one of the rock stars of concurrent and distributed systems. 2013 Turing Award winner Leslie Lamport created the language more than 20 years ago. Because he's a mathematician, it's the temporal logic of actions, but for short, TLA Plus. And it's fair to say that it's just a specification language. It's not a programming language. Yeah? You won't execute your TLA Plus specification. But we use it to design our distributed systems, our concurrent systems, our cloud systems, our microservice systems, before we have to implement them. And then once we've designed them successfully, the specification also acts as documentation that new people on the project can read to understand what the system actually does, how it does it, and what kind of guarantees it provides. And on top of that, at the icing on the cake, we get verification that can analyze our specification automatically, can analyze our design automatically, and check whether or not it satisfies our tests, our properties. Okay, if you're curious, you can learn more about TLA Plus at tlapl.us, and you can also study the extensive list of examples at examples.tlapl.us. And for those who like to follow up, there is a TLA Plus webinar coming up on June 14th. You can find the details on the internet easily. Just look for the Linux Foundation webinars. And with that, thanks for having me once again. I enjoyed it, and I'm looking forward to your questions.
Thank you, Markus. Please, a round of applause. I don't know if you hear the applause, but you're getting applause here. So we are using Slido, and we're going to get a couple of questions here. I don't think we can do side-by-side for Slido, right? Okay, so we'll keep the presenter up. So Markus, you're really huge next to me. I feel small. Okay, all right. So we already have a question. The first question is, if I'm not mistaken, the production code and its TLA Plus spec are separate things. How do we know or ensure that they do the same? Question mark.
Yep, thanks. Great question. I think it's pretty much the first question we always get when we talk about TLA Plus. There are a couple of approaches that can help you keeping the spec and the code in sync, which can be integrated in your CI/CD pipeline, and then during those tests, during those executions, you will find out if the spec and the code deviate from another. But zooming out, practitioners of TLA Plus, seasoned TLA Plus users, find it less important to to guarantee to make sure that the spec and the code are in sync. The value they get out of the specification outweighs this discrepancy. At some point, the specification is about modeling your system at a higher level, not at the level of the implementation. You leave out detail, irrelevant detail, that clutters your vision of the underlying algorithm. And then you have this artifact, the specification, at a much higher level that is orders of magnitude distant from the actual implementation.
Got it. So it's more useful to kind of design and architect with it to test things rather than actually have a copy of production, because then there are separate things for different use cases in that sense. Is that fair?
Absolutely. A copy of production, you don't want a copy of production, right? Because then you have the same mess twice. Beautiful.
All right. There's another question here. At what point would you introduce the use of TLA plus in your organization? Kind of similar note.
I think, yeah, there are two answers to this question. First of all, you want to introduce TLA plus as early as possible in the design cycle, in the development cycle. Ideally, at the time when you stand at the whiteboard and sketch out your system. That's the time to apply TLA plus. At that point also, the team working on a system is usually small, right? It's just a handful of people. You're not standing in front of a room with 100 developers. No, you have a small group of people who can apply TLA plus and study the design of your soon-to-be system at the level of the small specification.
Got it. And talking about design and all these new kind of multi-model tools, is there, in your knowledge, a tool that maybe you can design a distributed system and then run it through something that then the output is a TLA spec, TLA plus spec?
Well, the question sounds to me a bit like you want to use a graphical tool to design your distributed system. The problem with graphical tools is usually that they're very weak on the semantics. So you can probably sketch something out like a whiteboard design, but automatically translating it into a TLA plus spec or into any formal specification is probably an uphill battle. But because languages such as TLA plus are so expressive, usually translating this high-level whiteboard design into TLA plus is really not an issue. We saw it on the slide, it's just 20 lines of math. The non-determinism that's in the language makes this all easy.
Cool. Thank you. Well, Markus, before you go, I wanted to just show you on screen. We'll get this to you somehow from the people of Craft. You're going to get this little kind of drawing caricature. There you go. All right. Got it zoomed in. So thanks again, Markus. A round of applause.
Yep. Thanks for having me.